twice.
Only twice, which is remarkable.
2 injuries can only do that. That's great.
Oh my god. That is
You
not
know
how
those
it
are
works.
good organic chemistry debates. Bars.
Totally unrelated to my profession. Totally unrelated to my profession. All right, so to
that
kind of
better?
pick up,
So you are hitting him.
A bad one, I guess.
we're on YouTube now.
Are we though?
We will be. We will be.
Edit it out.
Okay, so OE2 reactions of substituted. Cyclohexanes. So last class we talked about, because of the ring flip and the prerequisites for having bonds aligned and anti to one another, that both the hydrogen and the leaving group, in this case the halogen, have to be in axial positions. So if halogen is equatorial and hydrogen is equatorial, and we can just, even if we have a pair of hydrogens here and here, even though this is going to be the most stable position for this compound because the chlorine is going to be out on the equator, so it's going to have fewer 1,3 diaxial interactions. If a base comes in and takes this proton, breaking this bond, pushing the electrons down here, they don't have anywhere to go to enter this chlorine, so this reaction doesn't take place. However, if we wait until we get a ring flip,
Are those different size arrows?
what's that?
Are those equal? Or are those one favored? Is the other reactants favored?
Reactants
Arrows.
favored?
Arrows
Oh.
the same size or is one shorter?
Oh, no, that's, well, it's not a reactant, it's an equilibrium between the two conformations.
Okay, but one of them's going to be.
One's favored, and it's going to be the one with the larger group on the equator.
Your chlorine's wrong.
Yeah, shouldn't chlorine be
Up on the second one.
Oh, thank you. The question was, is which one would be favored? And we get two different, okay, top one stays on top, bottom one stays on bottom.
Got it.
There we go. Man, bunch of critics this morning. First, I'm not good enough to be Liam Neeson. Second enough, I can't
Yeah, let's
ring flip while teaching organic chemistry.
Okay, let's be real here. You said that you couldn't be Liam Neeson.
You started it.
Fine,
I can't be Liam Neeson, but I can definitely push electrons back. Actually, I don't know. Liam Neeson might be able to push electrons. And then I got nothing on him.
Did you just call him pushy?
I don't know him. Most important thing, this thing happens, this thing doesn't happen.
Got it.
We reviewed, okay, this is review. Okay, good, let's get rid of this. So there's no more evidence that I can't ring flip this morning. -2 for Dr. McGill. Now let's take a look at what happens if we have this situation with neomethyl chloride. So we have an isopropyl group. We have chlorine, and we've got a methyl group. And if we were evaluating whether or not this could do an E2 reaction, what do you guys think? E2 reaction, yes or no? Yes. Okay. Because we have a hydrogen which can leave, and we have a chlorine which can leave. We also have, right? This one. So, what product should be formed? Predominantly. So hydrogen A is favored because it's going to lead to a product which is more stable because, nice, more substituted. So because I'm taking this off and this is rotating up to between the two positions, I'm going to draw it intentionally between the axial and equatorial groups or locations. And this would be the favored product for this ring. What if we do a ring flip? Okay, bottom, so it's going to stay here. And then that has to go top. What about this one? E2 elimination reaction?
This won't happen. Not parallel.
Nope, not for this one.
Wait,
Because-
wait. Well, wait for the CL in particular. But
Well, this is our leaving group, so it has to be axial.
Okay.
So it doesn't matter where the other where the protons are. So even though we do have a proton,
No, I read the CH3 as a CL3 and I got confused.
oh,
That
okay.
wouldn't have made sense.
Well, no. So
No.
no reaction. In this particular case, which of these two are more favored in equilibrium? The left, right? Because we have our bulkiest group on the equator, and these are similar, with this being slightly more bulky than chlorine. So even though this goes to the equator, we have two bulky axial groups here. So this is going to be, if you were asked to predict the product for this, this would be your answer. Now, let's say we have a different scenario. And in this scenario, now the chlorine is also on the equator. So with the chlorine having an equatorial position, we know now this cannot act as a leaving group in an E2 reaction, therefore no reaction occurs here. So if we do a ring flip, this should go up high. Stays on the... Okay. And which one of these is favored in equilibrium? The left is still favored in equilibrium because all of the groups are on the equator, and here all the groups are axial position. So this is not going to be favored. This is going to be less favored. However, the favored one can't do an E2. So what about this one? Can we get an E2 out of this?
Yes.
Okay, so we've got a chlorine, and do we have a hydrogen that can react with it? Bottom. So you like this one?
Yep.
Yeah.
Okay. So in this particular one, do we have any other hydrogens that can do the elimination? So we have to put the double bond between this carbon and this carbon. This is a terrible isopropyl group, but it's okay. So even though before, in the last example, we had the double bond butted to the isopropyl substituted carbon because it was more substituted, here we have to go to the less substituted carbon because we just don't have a hydrogen that's available in the axial position to do the E2 reaction. So you can't always just default to the double bond going to the more substituted carbon or system of carbons. You have to evaluate, do you have an axial proton that's available to do the elimination? Once you establish that you have it, if you have multiples, then you can pick which double bond is going to be preferred. So that's E2s. for an E1, let's do, could we do an E1 on this?
Why not? Because it's gonna be. Oh yeah.
What's the criteria for an E1 reaction? Tertiary. The leaving group attached to tertiary carbon? No? Okay. So, this isn't capable of doing E1. Throw in some methanol. Pour base, pour nucleophile, it's also the solvent. We have a tertiary halogen, so we're good to go for an E1 reaction. Doesn't matter what the ring, how the ring is oriented in terms of the flip. Probably not. Maybe. No. Solid no. We got a couple solid no's. Why not?
You don't have to worry about the
parallel.
position because it's
Concerted.
because the ion thing.
It was going so well, right up until it's like because of the ion thing. Yes.
Carbocation thing.
Because of the ion thing, it's a good leaving group, therefore it can, a minority of the time, spontaneously form the carbocation.
Thank you for the words.
No worries. That's why I make the big bucks. It's those words.
It's almost like I practically had.
Notice because we lose the tetrahedral structure here, we don't have, just like with the double bond, because we have this carbocation now, we don't have an axial and equatorial. I'm intentionally moving this methyl to between the two positions so that it's closer to trigonal planar than tetrahedral in the drawing. And it's because of this, now our base, which is water, can come in and do the elimination reaction. So this one doesn't matter. Notice I defaulted to the hydrogen that produced the more substituted product. Either of these two could have done the reaction also. However, it results in a less substituted product. Therefore, this will happen faster. Therefore, this one will be the predominant product. And once we've pulled this one off, this also goes to trigonal planar as well. So you would want to keep it in the axial equatorial position. You'd want to draw it in as trigonal planar also because it's no longer tetrahedral.
That's something where you're going to take off points if we forget.
Maybe a half point.
So don't do that.
Yeah. Yeah, that's why organic chemistry is so much fun, is there's so many ways that,
Points off.
yeah.
Why did you say that the base was water?
The base is methanol.
Okay. Equal water.
I'm going to gaslight the daylights out of this. Whoever's editing this, make sure you subtitle it with methanol. Yeah.
Because the chlorine, the leaving group can be in axial or equatorial positions, then you'll end up with the other chair conformer producing a different product.
It can't be a different product because you're going to be losing the tetrahedral centers at both locations. So which way it's flipped when it happens doesn't matter. You're going to have the same. You can do this the other way, but because you're losing any chirality, it's not an issue. Okay, so that's it for substitute cyclohexanes for eliminations. Any more questions before we start?
That chlorine on the left that's leaving, did you just not draw it in the base attacking?
It's a B1.
Oh, that was becoming the carbocation.
Everyone feel better now? Okay.
Are halogens the only thing that can act as leading groups?
No.
We're just only talking about halogens.
Yeah. Yeah, we're gonna
Don't make
I'm just gonna instead of jumping off of that cliff right now, there's lots of good leaving groups, and halogens just happen to be one of the categories that we start with. So, yeah. But we will have lots of good leaving groups down the road. Another question? Okay. Okay, so how do we start telling these things apart? Because we've got this scenario where we've got 4 different types of reactions that can occur with alkyl halides. So let's see, how do we predict reactions of alkyl halides? And specifically, we've got SN2, SN1, E2, and E1 reactions, and they all have their constraints and their different regioselectivity and their own stereoselectivities, or lack thereof. But before you can go down to those considerations, you have to know which one's occurring or which mixtures of them are occurring. So let's start with the broadest vision of it, and then we can go to more specific questions based on, well, we'll have 2 different scenarios where we have to worry about whether you have 2 things occurring simultaneously. So generally, if you have a primary or secondary alkyl halide, what are your 2 reactions that can occur? SN2 and E2. So this is big picture stuff. And generally, if you have tertiary you can have
SE1, SE1, not SE2.
And E2.
and
It's
good.
strong base is E2.
But not SE2.
None of this.
Got it. What would make something that's tertiary favor E2 over SN1 or E1?
A strong base versus a weakly basic solvent.
Right, so if you have a really good base or a really good nucleophile, which is acting as a base, you're going to get an E2. If you have the solvent acting as a weak base nucleophile, you're going to be getting one of these 2 or a mixture of them. So first thing to assess is always, where is your halogen? If your halogen is primary or secondary, you're going to start going this direction. If it's tertiary, you're starting to go this direction. Yeah?
I know they're rare, but what if you had some sort of solvent that was like a weak base but a strong nucleophile, or vice versa?
It's not that it's, we're going to have some scenarios that will favor elimination because you can't do substitution because of steric issues. So it's not that it's a weak base or a poor nucleophile, it's that it can't access the electrophile if it's bulky. So we're going to cover those scenarios specifically because that gives a little bit of control under some circumstances. But off the top of my head, I can't think of a great nucleophile that isn't pretty darn basic or vice versa. It's just whether or not that nucleophile can access the electrophilic attack for the specific reaction. So let's see here. Might as well just write that in here. So if you have a good nucleophile or slash base, you're going to be looking at being E2, and if it's poor nucleophile slash base, you're looking at E1 and SN1. So far you say, okay, is it primary or secondary? This way, tertiary. This way if it's tertiary. What's our nucleophile base look like? And that'll get you into the right categories. Let's start with SN2, E2. Any questions before we move into SN2, E2? No? Okay, so for SN2, E2, let's say we've got this primary twice. Now let's say we've got hydroxide, and in this case it's going to act as a nucleophile. In this case we've got hydroxide, and it's going to act as a base. We have these two different mechanisms. So for this one, you get a substitution reaction where this does attack from behind, kicking off the leaving group, and you get ethanol. In this one, this what is this one? Which one, how does this work? Somebody walk me through it. Are we pulling off this hydrogen or this hydrogen? Let's say A or B.
A.
Whoa! All right, we have descent.
It's the beta carbon.
There we go, because this is, yeah, that's actually A and B. So this is our alpha, this is our beta. So we're pulling off a beta. I can redraw this really quickly so that it mechanistically makes more sense. So we're abstracting this proton because of the base. That exceeds the duet. These electrons move to form the double bond, kicking off the leaving group. So we don't exceed the octet on this carbon. And that just gives us this as a product. So how do we tell the difference between these given this scenario? Well, first off, rules of priorities for an SN2 reaction, primary will favor secondary, will favor tertiary in terms of the speed of the reaction. For E2, tertiary will favor secondary, will favor primary. So if you're in competition and you have two different rates of reaction, if it's primary, like we have here, you're going to favor the SN2 over the E2. If it's tertiary, the E2 will be favored. And now everyone's like, but what if it's secondary? Everyone's not doing that. Like, that's not what everyone's thinking. What's up?
The SN2 can't do tertiary though, right?
Yeah, that's
so
why.
That just shouldn't be there, right?
Right.
You just-
Yeah, it can't because it's too slow. Doesn't happen. So yeah, you would be there. But in terms of general reactivity, we can say this is true. This is faster than this is faster than this because this is like functionally zero.
Okay.
So. Now there's, of course, there's exceptions, right? We'll come back to the secondary thing in a second. Of course, there's exceptions. So let's leave this here. So I'm going to say generally that so normally what would you expect to happen here? This is a normal circumstance.
SN2.
SN2, does it just like maybe confident? Who's now we have some time to think about it. What do you think? SN2. So when you do this product, I want everyone to think or draw what would the product look like if this is an SN2 reaction. This is important because it gives everybody a little bit of insight into possible syntheses down the road. And we're going to have a little bit of E2 here as well. But overwhelmingly, this is our favorite product. Just like we would expect because this is a primary, so highly favored. What about this one? Still primary.
E2.
Why?
Sterically hindered.
It's not the base that's bulky,
Bulky.
right? We have this bulky group over here. So to get rid of this bond, we have to do an attack here. Oh, sorry. We have to access this zone, and we've got these methyls. It's really easy when you see the methyls to forget that you have a whole other series of bonds with protons sticking out there. So as we start to add bulky groups around this, we make it harder to do this nucleophilic attack, and we're still going to have a little bit of this, but I think it's about 40% this, and then shifts to 60% this. Also note, because this is now a more substituted double bond, this is going to happen faster than I would have before, even though we're eliminating from a primary position. So that's another reason these bulky groups are starting to stabilize this mechanism. In this particular case, you would have a mixture of products. So you can have a steric issue with the nucleophile accessing the electrophile, and you can also have steric issues with the base. So if we have a non-sterically hindered alkyl propane, and we have T-butanol, which has been deprotonated to T-butoxide, that's a pretty bulky base. And that base is going to have a hard time acting as a nucleophile and accessing this because of all of this. So because of this, we are going to get a little bit of nucleophilic addition. Are we going to get some nucleophilic addition? No, it's doing this all wrong. 1, 2, 3. going to get a little bit of that, about 25%. And we're going to predominantly see the nucleophile act as a base in this case.
So those are all methyl groups attached to that second carbon.
Those are all methyl groups. Yeah. So this is a T-butyl alcohol with 3 methyl groups around quaternary carbon. I guess tertiary carbon because it's got alcohol, not another methyl group. But so yeah, T for tertiary. And then just like methanol can form a methoxide, you can form a T-butoxide, which is pretty darn basic. But in this case, it's also nucleophilic, but it just can't act as a nucleophile because it can't access the electrophile for this particular mechanism. So you have to take into consideration steric issues for both the electrophile and for the nucleophile / base. Yeah.
If you had a strong enough nucleophile, could you do some sort of good substitution onto a methyl or like a methanol? Not a methanol, a methane.
Methane is very, very, very not acidic.
Yeah.
So it'd have to be spectacularly basic. Spectacularly, like the kind of basic that would probably be reacting with solvent basic. Because think of a solvent and try to find a solvent that doesn't have a bunch of methyl groups in it, or other protons that are equally not as acidic. So you wouldn't be able to target your. So it's not uncommon. So there's all kinds of reactions where, let's say, one of the bases we'll use, which is a very, very strong base, are hydrides. A hydride is a hydrogen with a pair of electrons and negative charge on it. This is a very unhappy thing that really, really, really wants to give those electrons to something else. It wants to do that so badly that it is happy to aggressively pull water apart to form hydrogen gas and hydroxide. Because it is so much more basic than hydroxide, this reaction proceeds very aggressively. It does it so aggressively that it makes heat. If you use potassium hydride, this can create enough heat when you do this, where this will spontaneously ignite, creating a very large fireball. So there are bases that are able to pull hydrogens off of things we don't typically look at as being acidic, but then you start to react with things that you typically think of as stable. So there probably are scenarios like that, but then you're dealing with anhydrous conditions, you're dealing with reaction boxes which have inert gases in them, and like I said, there are scenarios, but it's definitely outside the scope of this class.
Does NaH cause that?
It's a slightly, it's less vigorous.
Okay, because it's like tells us in the book that that's what we're supposed to do to get our
Mhm.
hydroxide ion.
Yeah, so this is less vigorous than this
Okay,
because
gotcha.
of the counter ion. We were using this when that happened because it's more reactive, and we wanted that reaction to really, really, really go. But I think I told the story about the fireball on the ceiling, and no, I didn't.
Oh, the eyebrows.
Oh no, but the eyebrows were intact. So I have a colleague who at the time was doing his PhD, and he had just started, and he was doing this reaction, and you want this to be really dry because you're using all anhydrous solvents, and you don't want your hydride reacting with any water. So he puts this pile of potassium hydride into the vacuum oven, and we pull high vacuum and heat it for a couple hours to get it really, really dry. And it was weird because Fairbanks is typically pretty dry also, but it was middle of summertime. We had this rain, and then it got warm, and it was pretty humid in the building. And so what happened is he opened the vacuum oven a little too aggressively, and the powder, when it gets that dry, it's very light, and the air swooped in and lifted some of the powder and opened it up, and the moisture hit it and lit it off, and it started on fire. So what he did was not intelligent. He took the entire container of it and threw it in the sink, and the fireball hit the ceiling. It was pretty amazing. But it doesn't really smoke, because when you burn hydrogen gas, it's just water vapor. Yay. So it didn't set off any of the smoke alarms. We had that awkward moment where he's like, are you going to tell on me? Like, you're buying lunch.
You're telling like 40 people in here.
Well, he's been working in big pharma for a very long time. I'm not going to say where, because you could probably figure out based on graduation dates who he is at this point.
You're giving us more clues.
I know. Like, I'm not encouraging you to go find Daniel, but if you worked he's like, they can't take the degree away retroactively. Nobody got hurt.
You probably can't.
Much, except for egos. Okay, so let's see. What about secondary considerations? Bless you. In this case, the stronger slash bulkier bases slash nucleophile is going to favor E2. So if you want to favor the E2 reaction on a secondary alkyl halide, what you need to do is pick some of our classic strong bases or some of our sterically hindered bases. So if you wanted to pick a sterically hindered base to force an E2 reaction to take place, say as part of a synthetic scheme, what you could do is you could take the T-butoxide, is one of the classics. The book introduces two others. DBN, which is this 5-membered ring to 6-membered ring, which has nitrogen here and here, a lone pair and a double bond there. It also, there's a 7-membered ring up here variation called DBU. Any of these three would be excellent sterically hindered bases that are strong bases that can't act as nucleophiles well, and therefore will favor the E2 reaction. If you wanted to favor the SN2 reaction, what you would need to do is pick a nucleophile which is less basic, so that you are less likely to pull the proton actively off that beta carbon. And what that could look like is, let's see here. So this is acetic acid that's been deprotonated, so it's just acetate ion. Acetic acid has a pKa, so a 4.76, whereas say methanol 15-ish, about 15 and a half. So when you take this proton off, this, because this is such a poor acid, is a very strong base. So methoxide's an excellent base, and methanol is not a good acid. This acetic acid is a decent acid. It's not a strong acid, it's a decent acid. And when, breaking rules, and when you pull that proton off, you get acetate, it's a decent base / nucleophile. It's not a fantastic one. So this is going to be less prone to try to pull a proton off of a beta carbon and more likely to act as a nucleophile in a substitution reaction. So what would the product of this look like if you were to do an SN2 reaction with it? Give everybody like any one of those. What's the game show or the ding ding ding?
Is the oxygen with a negative charge going to be attached with chlorine plus? Can you tell?
Does it matter?
Yeah, it's.
Is this chiral?
Yeah,
No.
no, it's not.
Not, because we don't have 4 different groups.
Yeah.
So it doesn't matter in this case. Because this is the same thing if I drew the chlorine to the back and the hydrogen up front, because both of these are methyls. So in this case, it doesn't matter. But which of these oxygens attacks?
The negative one because it's farther out and it has.
It's farther out because it's got a longer, weaker bond.
Either of them?
Oh, yeah, it does go to negative.
No, the dotted line is just an approximation, but that's supposed to be double-sided arrow, not an equilibrium sign, because it's a resonance structure, which is why this happens so easily. So that's why it's harder to pull this hydrogen off, because this oxygen has to own all of the electrical charge if this hydrogen gets pulled off by a base, whereas if this hydrogen gets pulled off of a base, this electrical pair of electrons gets distributed equally between this oxygen and this oxygen. So both of these oxygens have partial negative charge, both of them have partial double bond character simultaneously, so either of them can do the attack, but it won't matter because you'll get the same product.
Does that do a thing where it increases the likelihood that it will react because it technically has 2 spots that it could
It doesn't hurt. Definitely doesn't hurt.
So how do you judge when the base becomes strong enough for E2 to dominate a reaction?
So just kind of by convention, if you're looking at your classic bases that you consider strong bases, your hydroxides, alkoxides, things like that. The bases you would classically look at from all of the examples we've been using as strong bases. So you have your alkoxides, hydroxide,
Are they always charged? Used for their base.
nearly always negatively charged because of extra electrons. So if we were to predict this, that'd be your substituted product. Now, if you wanted to drive this exact same thing towards elimination, you could just use methoxide or ethoxide or propoxide and get your elimination product. And that's pretty much all the considerations for SN2E2.
What's something about high temperatures? Is that right?
I'm not gonna.
Oh.
Yeah.
All these things from where they're gonna do it too.
I don't know. It could be on the ACS exam, but I'm not going to test you on it. Probably won't be though. Yeah. Why would it, actually no? This is good. This is a good opportunity. We're gonna improvise. How do temperatures affect the ratio of SN2E2?
Increases it.
Increases entropy.
Collisions.
Greater entropy. It makes it easier to overcome greater entropy.
So
So,
lowers the energy.
does it make it easier for bonds to break?
Yes, but it makes it easier for all bonds to break.
Okay.
So it is an entropy consideration. So if you're making more total products with one reaction than another, you're increasing the entropy of the system, or potential entropy for the system, which is not favorable. So if you're consolidating reactions, a reaction consolidates your number of products, that is entropically favorable.
So it drives towards SN2s with increased temperature?
Hmm?
So it drives towards SN2s with increased temperature as compared to E2s, which will have like at least one more.
Is that what the book says?
I don't know.
Favors it too.
It favors E2 because you're pulling off a proton and you're making another equivalent of you're taking the base and you're adding a proton to it and adding something to it. Instead of combining two things, you're making some new things. So it favors the E2 because it reduces the effect of becoming entropically unfavored. But it's a minor effect. So, and realistically, you're better exercising control with your strength of your base and your bulkiness of your base.
So we can't just add heat.
The thing is that's the other part of this is a lot of the time to get these things to go, these don't have really high boiling points if you're dealing with these solvents. So often you'll heat them to a gentle reflux or warm them to accelerate the reaction. So practically speaking, you're going to usually be adding a little bit of heat, unless this is a heat generating reaction that you have to keep cold, but these aren't those reactions. So of all the things to have to take into consideration, heat isn't one that I'm going to be adding to the mix. I don't think it's that's a really, really fine detail compared to the rest of it. I thought I was going to sneak away without having to talk about it. But big picture, everyone's going to be like, I'm not reading that section of the book. That's a whole paragraph that I'm going to not work on. So, any other questions? Oh, wow, I'm off the screen the whole time. This is fantastic.
Not the entire time, just when you sat down.
Okay, just sitting down. Any other questions regarding this before we move on to SN1 versus E1 on tertiary systems? Oh, okay. We got 20 minutes. This is doable. Okay, so we've got competition between SN1 and E1 in tertiary substituted alkyl halides. So let's see. Okay, so if this particular pair of reactions were to occur, what's our product for our SN1? Or just going to be doing our loss of our leaving group spontaneously because we have a good leaving group and we have a tertiary carbocation, so we can get this to form, and then we get a nucleophilic attack on that carbocation, and then we get a secondary attack which removes the proton. So I might as well just do it. So remember, when two things come together like this, the net charge for the system has to stay the same. This is something that people missed frequently on pushing electrons in the last mechanism, series of mechanism questions. Because this has a positive charge and this is neutral, when they come together, it still has to be net positive. So where's the positive charge go? This pair of electrons is coming over to satisfy this positive charge. However, this was neutral before it gave up its electrons. So now the positive charge is transferred to the oxygen. Oxygens are electrophilic, not particularly happy in this particular case. Now, what could happen is we could break this bond spontaneously, give the electrons back as part of a reversible process. But what happens faster is we just generate an acid. So we come in with a second equivalent of water, pick up that proton, break this bond, push the electrons to that oxygen. Now we're going to have our product plus hydronium. Because we've got our H3O plus now. And this, remember, is essentially equal to that in an aqueous system. So this is our product for the SN1. What about the E1? We can put the double bond here, here, or here. Does it matter which? No. They're all equivalent. So I'll just arbitrarily put it there. Now what ends up happening is the SN1 is favored here. 80%, 20%. And the reason is, and that's across the board for this particular scenario, and the reason is this is favored is because we don't have to break a bond to do this. We do and any of these 9 hydrogens are equally as accessible, but we do have to break a bond, to satisfy that positive charge once the base, this is looking like it's one step, but it's not, that's already gone, to do that reaction. So breaking the bond is slower because we have this really weak base. This gets outcompeted by this because we can just do a simple nucleophilic attack on the carbocation. So you're always going to have a little bit of elimination product as a mixture, but if you're asked to predict the major product for tertiary substituted alkyl halide is going to favor SN1. Now, this is good, because if we want a tertiary alkyl halide to favor the substitution product, we use this mechanism with a weak nucleophile / base and solvent, And if we want to favor the elimination product, we just use a good base and drive it through a different mechanism. So we have a tool for producing, based on tertiary system, either our substituted product or our elimination product. Yes?
Are there any conditions you can use to favor one reaction ever? Because it seems like it's always inferior to every other one.
Yeah, what kind of made it sound similar? Like there's like no chance. Like if you look at the end, like yeah, just defaults literally everything else. Like at the end of the chapter, where it just looks like this. It's like it's just not just the way.
No.
It's always just 20%.
Yep. But in chemistry, we don't typically think about just throwing things in water and have them react. So, but they do. So it's a justification of why we're seeing these other products. They're just not going to happen as fast as the other products. So it's not like it's a trace product. It's still going to be a fifth of the reaction. We still have to go through the rigmarole of cleaning it up on a column afterwards and purifying it. And if we were doing something industrially on like hundreds of gallon scale, this would still be productive.
I was just wondering, so are there any cases, like if we have all four, like you tell us to predict the reaction and we have all four to work with, is there any chance that there might be a no reaction? For any, like, is
That
there
has happened before.
dang it.
Can we see some examples?
That might help because there's like nothing like that in the book. Because it's like one of these four, and then there's like nothing for no reaction.
Oh.
Is there? I might be false remembering.
A really good, jeez. Maybe no reaction is not the best way to go. Bad reaction. Like if we were to put a great base/nucleophile in a polar protic solvent.
Yeah.
But that's when I used to handwrite all of the questions versus just using multiple choice questions for that kind of stuff. So I wouldn't stress that particular one. Like I said, it was a long time ago, and I've amended my expectations a little bit. So I think you could probably safely look for SN1, SN2, E1, or E2, and then predict the product with the correct stereochemistry and regiochemistry. That's probably hard enough. So one thing I want everyone to consider coming into this test. This is I need to wink so that these guys can see. This is an entire chapter on how to do reactions with alkyl halides. If you were faced with a synthesis question, perhaps you might need to know or remember how to make alkyl halides. All right, cool. So, hint dropped. Any questions before we call this fiend for the chapter? Yes.
When you're discussing various exceptions, what about the fluorine reactions? You talked the other day about how it changes which carbon is favored for a double bond because of the really strong electronegative character of fluorine that it doesn't want to take on.
Oh yeah, that's fair game. I mean, it's not high probability, but it's totally fair game. Fluorine as an exception is definitely. Whenever you see fluorine on a substitute alkyl halide question, it should trigger the exception part of your brain that says, whoa, something's different here than almost every example. Because I think every example on this board has used something other than fluorine except for when we're doing an exception on this chapter. So if you see fluorine, and it has to do with predicting a product with a particular substitution pattern, which double bond forms, definitely think less substituted for that product. other questions? Nope. Okay, we are done with this chapter. We've got the alcohol component of the next chapter coming up, and then organometallics, and that is going to be it for OChem 1.